Hey developers, Steven here from Be a Python Dev. In this video, we're going to extend our hash table data class that we made in the previous video a while back to handle collisions. Collisions is something that hash tables need to commonly deal with. For instance, in this toy example where we have size 3, if we insert 4 people into our hash table, obviously with only 3 slots in the hash table, something is going to hit into each other. In modern computer science, for most kind of toy programs that you might make, you're not going to really run into many collisions. And for that reason, you can always assume the ideal lookup time is 01. But in actual systems, if you have a hash table that has 1,000 elements, and you are using that to hold data for hundreds of thousands of users for like Facebook or Instagram, you're going to have a lot of collisions. Your runtimes aren't going to be ideal, and your code and program is going to be very slow. And hash table concepts are commonly used in databases to look up people. So if you're making a complex service, such as a database, you can see why you should understand hash table theories and properly dealing with collisions and lookups and dynamic resizing. This video will deal with the collision aspect. I might make a follow-up on dynamic resizing if there's enough interest, but for now, let's just deal with the actual collisions part. As previously mentioned, I moved the size from 10 to 3 so that we can insert 4 people and we can visualize what's going to happen. In actual computer systems where you're dealing with tens of thousands of people and you have a giant array, it might be hard to see immediately what's going on. For the purpose of understanding this a little better and more comprehensively, we're just going to use small numbers, small data, very basic data structures so that we can understand and see a little better what's going on. Our custom hash table data structure here that we did make in the previous video, if you're unfamiliar with it, has the common methods that you would expect. Initializing it with a custom size. Obviously, we would need to resize it, but this hasn't been implemented yet, so we're just going to raise an error in case anyone tries to call that. Getting the hash index, that is where we take the data and the key and run a hash function on it to convert that into the spot in the main array that we're going to insert our data. To do this, we're using the hashlib module, and we're taking the MD5 of the string and casting that into an int, and then running the module on that based on the size so that we're guaranteed to get a hash index that fits within the bounds of the array that we're using in self.data. Then the next pivotal methods that you need for your hash table: insert, get, and remove. Insert is going to be the main function that we'll be working with today. For example, if we insert Jim and we insert Steve and they both end up hitting the same hash, we're going to need to know how to be able to store both of those values in a way that they can both be retrieved. Obviously, if you have 1,000 values and they all end up hitting the same hash key, you're going to end up with something known as a hotkey in the hash table, and your hash table will actually be more like ON instead of O1. That's why it's important to have a large size hash table so that the keys are more likely to fall into different bins. And also that's why it's important to keep track of the size. And when the size starts to get, 50% of the total size or 150%, I'm not sure what the actual standard is, but then you would resize the hash table to get more slots, which would obviously take more memory within the computer to hold the empty data in the array, but it will ensure a more efficient hash table. Again, we're not worried about efficiency with this example, just kind of understanding the concepts. And for that reason, we're going to use size 3, and we're going to insert, maybe like 5 entries into this just to guarantee that we can see the hash. Then we have a key contains, which is not implemented, which is pretty valuable to be able to check if Jim is in our database, then change his data or something else. I think we can actually use this for a get, and we can move all of this logic into it to be a little more extensible. We'll consider refactoring it as we go on if that is required. Then the last bit of code here is to interact with our actual hash table. I'll copy and paste this into a paste bin. You can find that in the description so that you can put this into your IDE and play around with this hash table. Our demo code here creates the hash table. Then we create a data structure, Jim, which is just a tuple of a key. It's probably a username in a system, and we're assuming that this is a unique username so that there's not going to be two Jims. You could actually probably use the email address since email addresses are always the same. But again, if we're just assuming this first value is the username, and it has to be unique. That way, if we insert a new Jim with a new email address, we'd assume that maybe Jim just changed his email and that we're updating our data representation of who Jim is. Then we print the inserted data by showing the state of the hash table and the number of elements to show that it incremented after calling the insert method. Then we show the get method, which would retrieve that, and then ultimately the remove function. We probably will need to update the remove and the get function for this, and we'll want to make sure we do it in an extensible way so that we're finding the entries the same way between each ones. In that case, we will refactor it. And let's just run the code here to see what this is doing. Here you can see the initialized array that is holding the data for our hash table. It is populated with just zeros. If this was not Python, maybe it would be empty tuple objects where type is important. In Python, it's loosely typed, so we can just use anything for the placeholder values. After inserting Jim, we can see our hash tables array has been updated to hold Jim as the key and then the tuple as the data object, and then the two zeros. We also see the size was updated. When calling the get function, we see that we just get the value that the key represents. And then after calling remove data, you can see that we're back to what we initialized it with. For the purpose of collisions, we're going to need additional data. You can see if we make 4 different lines for 4 different people, that would make this code pretty hard to follow. To make it so the code is a little smaller, a little more lightweight, and more extensible, we're just going to put a container. We're going to have Steve, John, Jim, and Mark. Then we're going to update this for name in names. And we're not even going to do that. We're going to do name tuples equals. And this is going to be a list comprehension. So on our list, we're going to transform it into a new thing. And that's just going to be n. I think we want to use an f string here. n@gmail.com. We're just going to convert all of their names into names@gmail.com for the structure of what this address book might look like. For n in names. Now this should create a names tuples that looks similar to what this Jim did, but a little simpler than that. Now we're going to say for name in name tuples. Actually, at this point, it's not a name. It's a name tuple. Or it could just be name data. We'll just call it name data. We could also update this insert function since we're always doing the same thing where we're assuming the name is the key and then we insert the whole data structure. We're not going to worry about that too much right now. We're just going to keep this same pattern here. I kind of want to make this a little shorter, but for the purpose of good software development, we'll keep it as names that are easily understandable. If you have 1,000 lines and later on down here you see an ND. For that purpose, it's good to keep, good names. Insert using the key, and then the value is the second parameter to our insert function. Now, if we run this, we should see 3, maybe 4 elements here, but we're only going to see 3 because something is going to get overridden. And for this, we can just say get Jim as a string and remove Jim as a string, which if Jim is the one that's overridden, this may actually throw a does not exist error. Hash key does not exist. Okay, that actually is interesting. Jim was the one that did get overridden, likely by Mark. Which means Jim and Mark hash to the same value when run in our hash function and being modulo 3 for the size. You can see down here in our console, we have Mark, John, and Steve are all inserted, and Mark replaced Jim. We can dive a little deeper into this by removing Steve and Mark, or Steve and John. Then I assume when we run this again, Jim will get overridden by Mark still, to show that the previous values didn't actually impact why those two collided. Also, you can see down here the insert data shows the length was 4, even though there's only 3 in our populated table. Again, this is why it's important to handle collisions so that we accurately represent all the data that is inserted into our hash table instead of losing things and getting errors like hash key does not exist. Now I removed Steve and John just to prove that this should still kind of be the same thing. We can see Mark, which overrode the position of Jim, and then 2 zeros, which would have been our previous 2 names before. And we can also see that the size still thinks it's 2 because that line of code actually executed even though Mark overrode Jim. Now that we've run and talked through the example, let's go ahead and update the insert function so that we can get Jim and Mark accurately in there. We're back here at the insert function, which is just takes the parameter, the key, and the value, creates a tuple to represent the hash data, and then gets the hash index by calling our private getHashIndex function, inserts it into that spot in the array, increments the number of elements. Nothing too complicated there. But as we just saw with the case of Mark and Jim, Mark overrides Jim. For that case, we need to make sure that there isn't data already in that spot of the array. And if there is, we need to create a list of both the elements and put it in. To do this, we simply need to just check if self.data is 0. So if self.data hash index equals 0, we just simply insert it. If it's not 0, then we can assume it's a tuple and that something else is already in there. Which this makes a slightly interesting case if we have Mark and Jim both in the same slot, and then we remove Mark, it would still be a list, which might impact some of our other logic. But maybe that's okay. Maybe it's fine to keep it as a list. When we update our get and remove functions, we'll think through the implications of our collision handling logic that we're adding in. Now we know that this container needs to handle multiple objects. To do that, we're just going to convert this into a list. And that means we need to keep our previous data as a reference. So temp equals self.data. Well, if it's not 0, it could be a list or it could be a tuple. If it is a list, we just need to insert it into that list. But if it's a tuple, we need to take the data and turn it into a list. Which maybe it would just be simpler to store everything as list in general, and then we don't run into the complicated logic that we were just talking about. Which means it's important to keep it pretty simple. List is just a node and a pointer, meaning that we create a little extra memory reference for the pointer if we initialize everything as a list when we insert them. But I think that's okay. Our program's going to use a little bit more memory, but the code is going to be a little simpler and quicker to write. Meaning we are evaluating our trade-offs in our system, and we are accepting that this is okay. If we were on a memory constrained system where we don't want to hold the extra data as a list if it's not a list, then we would need to include additional logic to handle that. But again, this is just a small toy app. We don't really care about that. We'll just make everything as a list. Which means we actually need to insert this as a list. Now, for that reason, we can safely assume at this part that the previous thing was already a list and it's already been initialized because there's already something there. Which means that we can just do self.data hash index and call the append function and include our hash data here. So now that's it. We've handled our collision. We've changed everything to list. And everything should be good. All right, you can see now that we have Jim and Mark both in here. But you could also see that we had a hash key does not exist. And we had a couple errors here, which we knew about ahead of time because the lookup was previously looking at just a tuple object instead of a list object. To do that, now we need to update our get function to look through the list values and return those. Now let's update our get function to be able to retrieve Jim from our list of Jim and Mark. Previously, we were just getting the data at the hash index, seeing if the key for that matched the key that was entered, assuming all the keys are unique. And if the keys don't match, or the data is 0, we just return that the hash key does not exist. However, now that this data is a list, we need to do something slightly different. Which isn't really that bad. Return data 1. Okay, that was returning the tuple object, since it was a tuple with a key and a tuple in it. A little complicated, but if you watch it back a couple times, look through the console, kind of step through the code, it becomes a little easier to understand. And since data here is a list, let's update our variables to reflect that. And then for data in data list, we'll actually just do what we were doing before. And somehow we need to return this. This actually isn't going to raise, or it might raise before we check both the values. For example, we can see Mark down here. And if we were looking at Mark, we would see Jim first, and we'd see that this isn't Jim, and we'd raise this error. We don't actually want to raise this error yet. I think we want to update this logic to something like if dk equals key, return or data in data list. That's going to return, this is going to iterate on all of the tuples. Return data 1. I think this is okay. And then if we fall through our loop and don't find anything, then I think we can just raise the key error. So this logic is a little simpler actually than what we had before. Now we're just testing for existence instead of testing for non-existence. It looks like we are still getting the hash key does not exist, which means there is something slightly wrong in the logic in get data. We didn't update any of the logic, and actually it was just because we didn't save the changes. We can see in get data here, we actually are returning the tuple as expected. Remove data, however, is still throwing a hash key does not exist error. So let's update remove and let's refactor get and remove to use the same logic to get the index of the thing we want to return. And to do this little bit of refactoring, we actually need to change this data a little bit so that we return an index instead of simply returning the data, because we don't want to return the data in that case. We want to delete the data. And we want to make the get and remove function use the same logic, because if we extend our code and add on other extra functionality or rewrite another function that needs to get the index of something, we can actually just have all of that in the same function and only update our code in one spot instead of having to update it in multiple places. Okay, to make it so get and remove uses the same logic for finding the element to either return or to delete, we're going to create this private helper function using dunder get index. And we want this to take in the key, obviously. We also don't want the hash index. Let's name this a little more precise, get data index. And this will return the index if it exists. Otherwise, we can just have it return -1. That way we can check our value there. Or we can just have it return none. I think none evaluates as falsy. Yeah, I'm pretty sure it does. All right, we have our hash index. We have our data list. Maybe this should return a tuple object if it exists. That way we don't want to have to look up the hash index again. Otherwise we won't really know what's going on. And we want to change this to be enumerate. That will turn data into an index instead of the actual index. So let's use data index. And then we'll turn this into data equals data list at the data index. If this comes back as 0, enumerate is going to be nothing. Let's actually just handle that case. If data list equals 0, return none. For data index and enumerate, data, blah, 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 return. And we were going to turn this into a 2-dimensional object of hash index data list. Actually, data index. All right, so if you don't understand what this code is doing, please do copy it or write it down and try calling it a couple times and start to grasp what it's doing by stepping through. Otherwise, I'll just quickly explain it. Here we're getting the hash index based on the key inserted. We're getting the value at that entry in our hash table, and we're storing that into data list. Data list could be 0 if nothing is there, and we check that and we return none, because the assumption is if we're not finding anything, get data index is just going to return none. Maybe we'll call this get data index tuple just to be a little more specific. And when you're using a high-level language such as Python, the more specific you are, the easier your code will be to maintain and develop over time. Then if data list isn't 0, we assume it's a list. And in that case, we're able to enumerate it. During the enumeration, we take what the data is at that index. We pull out the 0 value of that tuple, which is a key, and we check if the key equals the key inputted into the function. If that DK does equal the key, then we can return the 2-dimensional tuple that has the hash index and the data index, which will allow us to either return our data or to delete our data. Now that we have this, we can use this function instead of doing this. Now our data index equals self dot our private function get data index tuple. I guess we can call this the dip, the data index tuple, which is actually the dit. And we will pass in our key into this. If dit, that means that we've found an index. We can just do self.data return, which is a two-dimensional array that also has a tuple. So it's kind of multi-dimensional, a little hard to grasp. That's why this might take a little while to understand. Play back as you need to, or ask any questions in the comments. You can also simplify this a little bit by not using a tuple, but I think for this example, it makes sense once you look through it enough and kind of grasp what's going on. But here, self.data 0, and then how do we look up a multi? Then I think it's this, and then it's 1. So again, triple dimensional, a little mind-blowing to grasp the head around. And we return that if that does exist. If it's none, we raise the key error. This will make cleaning up the remove function a lot easier. List indexes must be integers or slices, not tuple. This is in our get data index function. I'm pretty sure the enumerate function turns this into an integer. Let's just print our data index here and see what it thinks it is. Okay. Enumerate actually, it needs to be separated. I forgot about that. Enumerate returns a tuple. So you can cast that into two different variables, one with the data index and one with the actual data that's there. That makes it so we don't need this lookup right here and cleans up this function just a little bit. Okay, now we should be good. Get data is returning Jim, just like it was previously, but now it's using a common function instead of specific logic. And this common function is useful because now when we need to update remove, this will be even easier to do. We can just get rid of all this. And if we are removing the last element in the list, we actually need to, okay, yeah. Because if the list is one person and we are removing that last one person's data, we need to reset it to 0. If the list has 2 or more people in it and we're just removing that one index, that's perfectly acceptable. That's fine. We don't need to do anything special. And that's actually the easy thing to do. So to update our logic for this, let's use our fancy helper utility function that we made here. We change all of this and remove. We still need this key error. If not dit, so that means that the data index tuple was not found. This equals none, raise the key error. If it is found, that's good. So now we can do something fancy where if self.data dit1 and the length of this element, so this is just the list that is holding our collisions. And if that list only is 1 and doesn't have any collisions, then we just want to reset it to 0. And our hash index is now stored in dit0, and the list index, or the collision list index, is dit1. If the length is not 1, then it's obviously greater than 1. So our else for this will be this. And I think you just remove from a list. I think there's a remove function. We can test this out by going into Python console. Test equals 0, 0, 1, 2. Test.remove 1. And that was actually a really bad example because I don't know if it removed the key or if it removed the index. So now we can redo this. Okay, it looks for the specific value. What if I do this? Okay, so we want to use del and not remove. The remove function needs the whole data object, which we can use, but it's slightly more complicated to do. But it's a little easier to just delete that entry in the list completely using the keyword del, and then self.data dit0 and then dit1. So again, dit0 equals the hash index, dit1 equals the collision list index. And then we decrement the num elements, and then we just respond with none if the thing succeeded. We can also return true, and then you can do things in your logic like if remove, assumed it was removed, and be happy. Since we're using a key error here, we probably don't need to do that. But now, let's run our code. Everything should be happy. We are using a list to deal with collisions instead of just storing our data tuples directly. And we updated our get and remove functions to look for the collision list instead of looking for the single element. All right, insert data. Jim and Mark were both inserted into the 0 index slot of our data array. Getting data looks through the collision list and finds the key that matches Jim and then returns that data tuple. Then remove data looks for the key that matches Jim and removes that element from the list. Let's also add in an extra line here to remove Mark to show that we are reinitializing our value to be 0 by checking the length of that list. Now you can see the first call of remove data removes Jim and leaves us with Mark. The second call removes Mark and reinitializes to 0, 0, 0. And our length should actually be 0 as well. Let's print that too. Which is important for our resizing function that we will do in another video. And you can see now our length is 0 and our length was previously 2. Now everything in the code is updated to handle collisions, and this should make our list a lot more extensible. Let's go ahead and show that by adding in Steve, Tony, Jimbo, Jim Bob, Havana, Rajesh. We go ahead and exit this. Let's get rid of some of our remove data and get data code just to clean this up. Yeah, that's fine. Exit, because that was the wrong thing. All right, and you can see here we have Jim, Mark, Tony, Havana, all in the same index. Jimbo, Jim Bob, Rajesh, all in the same index. And then Steve is in a container by himself. I guess he has a unique hash index. And I will go ahead and copy this as is. Actually, let's get our get data function back in there and our remove data, which this will actually be a good use case to show everything's doing what it should. When we do our get data, we're still getting Jin. When we do our remove data, we're calling it twice. Mark was there. Now it's just Tony and Havana in the first slot or the 0 index of our hash tables array. And the length is 6 instead of 8. And I think this actually worked out great. I hope you guys learned something. Thanks. Please do subscribe if you made it this far. And if you have any videos or things in computer science that you would like to see more about, please leave it in the comment. See you guys later.